Right, this is the final Pendulum update. The software problem from last time has been fixed, so the controller now pushes the pendulum at every swing, and this has achieved a 0.8 meter swing size. And just for the record, all these tests are with a pendulum 2.55 meters long, comprising a ½ kilogram connecting rod and a further ½ kilogram weight for the bob. And now I've had a chance to study it in action, I realise the original target of 1 metre is definitely overkill, and something like half or even a third of a metre would be much easier on the eye. And for comparison, our wind-up wall clock has a 35 centimetre pendulum, which swings about 4 centimetres, and if you scale that up to 2.5 metres, the swing would be about 0.3 metres. So that seems to tally, assuming my sums are right. Now, reducing the swing is easy, a lot easier than increasing it, but this gave rise to a new unexpected requirement. The actual force or effect of each push needs to be variable as opposed to fixed. Now, previously the controller just disabled the push when the maximum swing was reached, and this worked fine, except that I now realise the sound generated by the stepper motor is effectively the tick of the clock, similar to a conventional escapement mechanism but without the tock sound, and stopping this every now and again spoils the illusion. So I needed a way of pushing, but not as hard. The other factor is the tick volume. And using full steps on the motor produces quite a loud sound, which may be acceptable given the height of the clock, but it would be nice to have something quieter just in case. And I found that now the timing is more precise, half steps or even quarter steps are sufficient to maintain smaller swings, and these are quieter than full steps. The trade-off is less torque, as discussed earlier, but if this is insufficient to start the pendulum from rest, we need a stronger push at the start. So how can the power be varied at different times by the software? Well, adjusting the microstep factor needs extra I/O signals from the controller to the driver chip, so this is a last resort option. Other ways are to adjust the number of steps per push, the time between these steps, and the timing of the push relative to the swing start position, and all these can be controlled by software alone. Now, calculating which combination of these is best was too much for me to predict, so I did the usual thing and made them all adjustable with a menu. The final values can be hard-coded later into the target system. They're split into 3 groups, prefixed by S, I and B for the 3 different states. The S values are applied when starting up from rest, and this allows a higher power, if necessary, to start getting useful readings from the sensor. The I values are applied when the swing amount crosses the start-up angle threshold and allows a medium power to keep the pendulum idling or ticking over, if you'll excuse the pun. The B values are applied when the swing amount reaches the maximum angle threshold and backs off the power to allow the swing to decay. And once it drops below the threshold, the idle values are reapplied. So for each state, we have the number of steps per push, the number of milliseconds between each step, and the number of milliseconds offset from the swing reference point. The microstep factor, 1, 2, 4, 8 and so on, is not implemented yet, as it would require extra I/O signals as explained earlier, but there are jumpers on the breadboard for testing each factor manually. The 7-segment display now shows the current swing size in 2 formats. The left side shows rotary sensor units, and there are 4,096 units per revolution, and the right side shows the swing size in degrees. As an example, the original 1 meter swing equates to 23 degrees, so a 0.3 meter swing should be about 7 or 8 degrees. So you can happily while away the hours by changing settings on the fly and seeing how they affect the swing. Now, I did find the swing amount is self-limiting depending on the settings, so the back-off state may not be needed. The first example maxed out at 0.8 meters using multiple full steps per push, and these examples show smaller swings using fewer steps per push. Here's a close-up of the clutch drive in action, although there's not much to see as it's so compact now. From this viewpoint, a clockwise rotation of the motor pushes the pendulum conrod forwards. The red coupler is fixed to the motor with black grub screws, and you can just see these creeping anti-clockwise as the pendulum nudges it back on the reverse swing. And finally, if you're still with me, here's a full power-on sequence using 6 half steps for the start, 2 half steps for the idle state, and it maxes out at about 0.4 meters, so the back-off values are not used. I hope the top-down shot was worth the risk to life and limb. I was at the top of an 8-step ladder, grappling with lighting and a camera tripod on the shelf, which was way too narrow. But you can see the display and pendulum all in one shot. Ignore the first few diagnostic numbers. It will show 00 when the sequence starts. There are 3 coloured lights which indicate the 3 states. Green represents the startup period, blue is the idling period, and red, which is not used in this example, is the back-off period. The startup threshold is set to 3 degrees, so you'll see the blue light turning on when the swing angle exceeds this. You can hear the change in tick sound due to the different number of steps per push. It's now reached the maximum swing for this particular idling power, so it will remain in this state from now on. And just for completeness, here's a quick view from ground level. Okay, that's the end of the pendulum tests, finally. I'm happy with the behaviour, and it just needs a long soak test running 24/7, so it may be a while before the next update to this series. Thanks for watching.